Welcome, Marissa. All right, we're up and running. So last time we had this 4-6. The problem was the problems are quite lengthy. So while I probably can't practically go through any problems completely, I wanted to ask if there were some hang-ups, some technical difficulties with lesson 4-6. This was the one where we were putting all the graphical techniques we have together. A summary of curve sketching. 4-6 questions. To all four of you. All right, we're sounding pretty clear, so let's get started on 4-7. One of my favorite topics, again, we've done this once before. Optimization problems. Finding the absolute best, let's see. For example, finding the maximum, not like close, but exactly or finding the minimum, that kind of thing is involved in optimization. So I'm going to start with a classic problem, one that is in just about every calculus book you'll ever see. And this is problem number 2 from the 4.7 lesson. So let's just get into it here. Numerical, graphical, and analytic analysis. An open box of maximum volume is to be made from a square piece of material 24 inches on a side by cutting equal squares from the corners and turning up the side. So you cut out a little square, which in the diagram is labeled X. Cut that out, and then you fold up the remaining sides, and then fasten glue or whatever, but that'll give you an object like you see on the right here. So the question is, and I'm going to go right, they've got all this preliminary stuff, but I'm going to go right to part C. Use calculus to find the critical number of the function in part B and find the maximum value. So in other words, what is the size of X, that little X corner, 2 by 2, 3 by 3, whatever it is, what's the size? What's the size that will maximize the volume of the box? Volume. I'm going to mute Jordan so we don't have this interference. All right. So that's the problem. So it's really a volume problem. And how do you find the volume of a box? Well, the volume of a box is what? Length times width times height. It's 3 dimensions. Now, in the case of our picture, you see what happens is when you cut X out of the corner, of course, there are 2 corners cut out, and that makes the remaining length 24 minus both X minus 2X. And that's the same thing that happens. Because it's a square, it's the same thing that happens with the width. So, all right, so volume. Let's get this thing going here. So volume is equal to the height of the box, X, times the length, times the width. Okay, so that's the volume. All right. Now, let's get this multiplied out here. So first, let's do the 24 minus 2x times 24 minus 2x. So 24 times 24, we're 576. So 576. 24 times negative 2x minus 48x. Negative 2x times 24, negative 48x. Negative 2x times negative 2x plus 4x squared. Okay, we got to multiply all of that by x. And I'm going to put the, in descending order. 4x times x is 4x cubed. Then we have negative 96x multiplied by x squared plus 576x. All right, so that's just multiplying it out. So there's our formula for volume. Now, we need to what? If we want to maximize this volume, we're going to have to take the derivative. Welcome, Jamie. And we want to set it equal to 0. So v prime, first derivative, 12x squared minus 192x plus 576. And of course, now we want to set that derivative equal to 0. So we can factor, I believe, a 12 out of there. So 0 equals 12 times x squared. So 192 divided by 12 is 16 minus 16x. And 576 divided by 12, 48. Can we factor this any further? We can, because, let's see, that's x minus, let me think. So we got to add up to, so that could be 12 times 4. Yeah. So minus 4 and x minus 12. Right? If you multiply that, negative 4 times negative 12 is plus 48. Negative 4x plus negative 12x is negative 16x. So that works. Okay. So now, why it's set equal to 0. So what do we need to get a 0? Well, this is never going to be 0. But one answer that'll work is x equals 4. And the other answer that would work is x equals 12. Now, think about 12 for an answer, would you? What would happen if we cut 12 inches out of the corner of each of the 4 corners of this box? If we cut out 12 inches from each side, remember, it was originally 24. That means the bottom is gone. So you're going to have a completely collapsed box, and that's not going to work. So even though we did the algebra right and everything, from a practicality standpoint, we have to reject that. The other answer, that's it. That's the perfect result. So if we cut little 4x4 squares out of each side, that'll make the box a height of 4, and you take 8, so the bottom is going to be 16 by 16. So what will the volume be? So let's just say, what's V of 4? The reason I'm asking that is because you see how it says find the maximum volume in the problem. So what is V of 4? Well, it would be 4 times what? 16 times 16, 256 times 4, And that's what, cubic inches? These are inches. Yep. So there are two answers to this. What's the perfect size X to cut out? Answer, a 4-inch square. And what is the maximum volume you'll ever get out of this 24 by 24 piece of material? Answer, 1,024 cubic inches. You will never be able to best that with any other dimension. So again, classic problem. Most people know how to find the volume of a 3D object, length times width times height. Maximize, smacks of first derivative, set first derivative equal to 0, solve. Questions? Okay, so that's kind of sets the tone for the kind of problems we have. By the way, all the problems I'm going to do are from the assignment. So I mean, there's really nothing new here. We're just applying techniques that we have learned. So here are some of the problems. I don't know if we're going to do all these, but these are right out of the book. Find, so let's start with number 4. You've got, it says, please note this. Find two, got to get a pen here. Find 2 positive numbers that satisfy the requirements. So really important that you remember the constraints of this problem. Any negative answers we get, we're rejecting those because we got to have positives here. Okay, so number 4 says find 2 numbers, positive numbers, whose product is 185 and the sum is a minimum. Okay, so we got to set this up. In the beginning, you can start off with 2 variables, x and y, but only in the very beginning, because you know that when we differentiate, we want to always differentiate with respect to x. Well, I suppose we could do implicit, but we want to get it down to the point where we're just working with 1 variable. So to start off with, we're going to say, all right, let's call these 2 numbers x and y, and their product, x times y, according to the problem, is 185. All right? But I don't want 2 numbers, so what we'll do is we'll take this xy equals 185 and we'll solve it for y. And of course, you just divide both sides by x, and you get another name for this second. Instead of y, we could just call it 185 over x. So now we're at this point where, if you look over here on the left, our 2 numbers are x and 185 over x. All right, so now we've got our naming taken care of. Now let's go back, and what's the problem asking us to find? And the second part of that is the sum is a minimum. So we need to add these 2 together and then do the calculus. All right. So there's our 2 numbers, x and 185 over x. So let's first add them together. So in blue, x plus 185 over x. And in green, you can see I was starting to get ready for getting a common denominator so that we could get that expression together. So you can see I could achieve that by multiplying that first fraction by x over x. All right, that gives us a common denominator, and we can bring it together as what? X squared plus 185 all over x. All right. Yeah, I don't know why. I guess that I decided to leave it unsimplified. So x plus 185 over x. Take the derivative. All right, take the derivative. Derivative of Oh, first I rewrote 185 over x as 185x to the negative 1 power. Take the derivative. Derivative of x is 1. And then use the power rule on the second part. Negative 2 times negative 1 is plus. I'm sorry. Yeah, I was already taking the derivative. Negative 1 times 185 is negative 185. Reduce the power by 1, x to the negative 2. Okay, so there's my derivative. Set the derivative equal to 0. And what's another way to write negative 185 x to the negative 2? Negative 185 over x to the 2. All right, set it equal to 0. Can we solve for x now? Yeah, that's not too difficult. So add 185 over x squared to both sides gives us that. Multiply both sides by x squared. Take the square roots of both sides. And there we have two numbers that will work. Plus and minus the square root of 185, 13.6. Now, we have to reject the negative because, remember, we were only looking for positive. So 13.6 seems to be, what was it, the minimum? Yeah, we were supposed to find when is the sum a minimum. Now, let's just take a look at that in Desmos and see what that looks like. X plus 185 over x. Okay, we got to zoom out to see this. So if we zoom out far enough, you can see, actually there are two parts to this curve. But this this thing down here is when x is less than 0. And we already know we have to reject that because we only want, this problem only wanted positive numbers. So let's see. Yep, sure enough, 13.6 is the point where we reach the lowest, the minimum. And so you can see our problem is correct. Any questions? So that was what? Number 4. All right, let's go on. Next, we're going to do number 6. By the way, I will sneak an odd or two in here, and then we'll take a look at the assignment when we get down to the bottom of that. So, here we go. The second number is the reciprocal of the first number, and the sum is a minimum. So we have a minimum sum again. But that second part, the first part, the second number is the reciprocal of the first number. So when we pick our two numbers, x and y, the second number, y, is the reciprocal of the first. So y equals 1 over x. Okay? So the two numbers are x and 1 over x. Their sum, x plus 1 over x, is a minimum. So take f of x. We're going to rewrite it as x plus x to the negative 1 power. No shock. We're going to take the derivative. Derivative of x is 1. Here we can use the power rule. Negative 1 times x is negative x to the negative 2, which I rewrote in with positive exponents. All right. Set the derivative equal to 0. And then just do enough algebra to get that solved. Add 1 over x squared to both sides. So I didn't write it down, but there are really two answers here again. 1 and negative 1. Again, we reject negative 1 because the problem, this whole bank of problems is only about positive numbers. Okay, so if you take 1, all right, we got 1. Where did I get this 1? Well, what's the reciprocal of 1? 1. So what are the two numbers? Let's see, how did we state it? What are the two numbers? 1 is the reciprocal of the other. That when you add them up, their sum is a minimum. And here they are, 1 and 1. And the minimum sum, of course, would be 2. So, final answer is over here. Okay. Questions? All right. Anyone? 1, 2, 3, 4, 5. Only 6 of you here. All right. Next, let's go to number 7. So here's one. Here's our odd problem. One of them. Number 7. Find two positive numbers so that the sum of the first number and twice the second number is 108, and their product is a maximum. All right, so the sum of the first and twice the second number is 108. All right, so if we say, all right, the two numbers are x and y, the first, x, plus 2 times the second, 2y, equals 108. Now we don't want a y, so let's solve for y. So I subtracted x from both sides, and then I divided both sides by 2, and I got this expression. The second number is -1/2 x plus 54. Okay, so now I got my two numbers, x and -1/2 x plus 54. Now what? The product is a maximum, the product. So I need to multiply my two numbers and set up a product. There it is. The first number, x, multiplied by the second number, -1/2 x plus 54, equals, whatever the function is. All right. So multiply that out. -1/2 x squared plus 54x. Now let's take the derivative. Kind of cool what happens here when you take the power rule. 2 times -1/2 is -1x. Reduce the power by 1 to the first power plus 54. Set that equal to 0. And x equals 54. So where did I get the 27 from? Well, you take the 54 and you plug it in, to the second number. -1/2 times 54 is -27, and -27 plus 54 is +27. So what are the two numbers? 54 and 27. Want to just check it? The sum of the first number, 54, and twice the second number is 108. So this plus 2 of these, that's 108. Any questions? All right. Let's do number 8. Each one of these is a little bit different and has some interesting things to watch. So here's number 8. To find two positive numbers so that the sum of the first number squared and the second number is 54. And then their product is a maximum. Okay, we've been doing minimums, so here's our first max. So here they are. The two numbers will start off with x and y. The first number squared plus the second number is 54. So x squared plus y equals 54. Again, we don't want a y, so we're going to solve for y. Subtract x squared from both. So here's another name for y. So what are our two numbers? They are x and 54 minus x squared. Now we're ready to do, what does it say here? The product. Product is a maximum. So now we need to set up a product function for those two. And there we are. So take the two numbers, x and 54 minus x squared, and multiply them. Okay, we've done that. Multiply that out. 54x minus x cubed. Take the derivative. What's the derivative of 54x? Is 54. Power rule on negative x cubed, negative 3x squared. Set derivative equal to 0. Solve for x. So let's subtract 54 from both sides. No, let's add 3x squared to both sides. You could have done it the other way too. Divide both sides by 3. And take 2 square roots. Actually, I'm ignoring the negative square root because of the positive number requirement. So the square root of 18, which is what? 9 times 2, and the square root of 9 is 3. So 3 times the square root of 2. That's the one number. What's the other number? You come over back up here where the underlined red is. Muting. Okay. So anyway, now back up here. Let's see, try to get these on again. All right. So if you take 3 times the square root of 2 and square it, what do you get? You get that 18 that we had down here, and 54 minus 18 is 36. So the two numbers are 3 times the square root of 2 and 36. So you don't always get nice integer numbers, but those are exactly the two numbers that we needed for this problem. Any questions on number 8? Speak up. This whole idea of this is a two-way audio, and you should be able to. If anything's not clear, just let me know. That's what we're on for. Okay, we're going to number 9 next. Another odd problem. Okay, so this is a new section now in the assignment, and it says maximum area. In exercises 9 and 10, find the length and width of the rectangle that has the given perimeter and a maximum area. So number 9 says the perimeter is 80. So if you have a rectangle whose perimeter is 80, tell me what you can do to make the area a maximum. Okay. So how do you find the perimeter of a rectangle? 2 lengths plus 2 widths, right? Got to go around both 2 lengths and 2 widths. So 2L plus 2W equals the amount they gave us, 80. Okay, we have 2 variables there, L and W, and we'd like to get rid of one of them. So, same old deal. Let's solve for one of them. Let's solve for W. So subtract 2L from both sides, divide both sides by 2, and there we have an alternate name for W, 40 minus L. And if you look over here on the left, we now have, those are basically our length and our width. And we have only one variable, which is good. So now, now the rest of it is, if you look up to the top here, the rest of it is an area problem. How do you find the area of a rectangle? Length times width. So we need to set up the product of those two, multiply them, and that's basically our area. Okay, multiply that out, we got our area. 40L minus L squared. Now, you know by now, if we're going to find the maximum, we got to take the derivative. Very easy derivative, set the derivative equal to 0. And then we should be able to, with a little bit of algebra, solve for L. Okay, so the length of this rectangle is 20. Now you tell me, if the length is 20, what's the width? You look up here, what's 40 minus 20? 20. So in other words, it's 20 by 20. So for this, you're going to find this is often true. When you want to find a maximum or a minimum and it deals with a rectangle, it almost always turns out to be a square. And you see how here it did? 20 is the length and $20 is the width. So once again, you'll see this often happens. This almost always happens with a square. I mean, with a rectangle, that it turns out to be a square. All right. Now we're going to enter into a level of complexity here in the next step. This time we're going to do number 10. And you'll see that number 10 has an extra challenge to it. At least that's the way most students seem to react to this. This time we're told that the perimeter is P. Yeah, it's not a number. So the perimeter is P. And they still want you to do the same thing. Find the length and width that will make that rectangle that has a perimeter P into a maximum area. All right. So this time, when we do the perimeter, 2 lengths plus 2 widths, I just made a little sketch. So when I find the perimeter, this time it's not 80, this time it's P. Now P, throughout this problem, is what? A constant. We don't know what it is, but we do know it's a constant. So let's first get rid of what? Let's get rid of the W. So take the equation and get the L on the other side and divide both sides by 2. So now I have a name for the width of this. And that's still only got one variable in it. Remember, P is a constant. So now we have the length is L and the width is P over 2 minus L. I mean, all I did was take P divided by 2 minus 2L divided by 2, and I just wrote it as P over 2 minus L. Everybody see that? Okay, so multiply it out. Okay, so I got to remind myself, what did I do here? So I just multiplied. L times P over 2 is P over 2 times L. That's to the first power. And L times negative L is negative L squared. Okay. What's the derivative? P over 2 times L1. Well, the constant's there. And the variable's gone. And negative 2L. Negative L squared. The derivative is negative 2L. Set derivative equal to 0. You want to find out what? Yeah, you want to find out the length. So we put 2L by itself. We divide both sides by 2, and we find out that the length needs to be P over 4. Think about what that means. I wrote it out here. But I mean, if the length of the rectangle is P over 4, that means the other length is P over 4, which is P over 2, and that leaves P over... So in other words, this has become a square. When is it that a fourth of the square is the length? Oh, when it's a square. Yeah. So let me just, so what's the length and the width? I've got the length. The width is also, let me write this out. The width is also P over 4. So if you take two lengths, you're going to have 2/4 or a half. And if you take two widths, you're going to have 2/4 or a half. And a half plus a half is the whole. And you've got your perimeter P, like the problem began. So even though the problem didn't have a number for the perimeter, we were still able to do the problem and make sense out of it. Any questions? Let's go on to number 12. So here we go, different section. In exercises 11 and 12, find the length and width of a rectangle that has the given area and a minimum perimeter. So this time we're given the area and we have to find the perimeter, minimum. And again, look what they did. They gave you the area is A square centimeters. So once again, just like with P for the perimeter, that A is some constant, but we don't know what it is. That's the area. Okay, so we got our length and our width, and this top equation here says it, right? If you take the length times the width, you get A. All right. So let's get rid of W again. Let's divide both sides by L. So here's this expression for W equals A over L. Okay, so now, what are our two dimensions? The length is L and the width is A over L, like we just figured out. Okay. Now, make this into a perimeter problem, because that's what this says. All right. How do you find perimeter? Two lengths plus two widths. Yeah. So here I am. Two widths, 2 times A over L, plus 2 lengths. That should equal the perimeter. Okay? I just rewrote that a little bit. Remember, A is a constant. A is a constant. So I put the constant out in front, 1 times 1 over L, which is L to the negative 1. So there it is. Now let's differentiate. Left side, negative 2A, L to the negative 2, plus 2. Set derivative equal to 0. Again, I wrote L to the negative 2 as L squared on the bottom. Subtract 2 from both sides. Remember, A is a constant, so we're trying to solve for L here. So here I did what? Cross multiply. Negative 2A times 1 equals negative 2 times L squared. Divide both sides by negative 2. And then take the square root. Okay, so the length is the square root of whatever A is. Well, what does the width have to be? I mean, think about it. The product is A. So the question is, think of it this way. There's your length. We just figured that out. Times what do you have to do that to get A as an answer? Oh, yeah. Well, that would have to be the square root of A. If you take the square root times the square root, you get that thing without the square root. Okay, so now I can see both the length and the width. Okay, then I have a pretty challenging problem for our last one here. Okay, so let's dig in. It's number 21. Yeah, here's the problem in the book. So we've got a Norman window, which is what you see, a rectangle with a semicircle on the top of it. And for all practical purposes, you can ignore the cross piece here. You know, this little piece of wood. You can pretty much ignore that and think of the glass as all being together. So the idea here is a Norman window is constructed by adjoining a semicircle on top of an ordinary rectangular window. See figure. Find the dimensions of a Norman window of maximum area if the perimeter has to be 16 feet. So the perimeter of this window has to be 16 feet. All right, so that's how we're going to start. And then once we've got that perimeter nailed down, then we're going to work on getting the area maximized. All right, so we've got a two-part problem again. So here we go. So there's a sketch of our Norman window. Rectangle, red, along with the black semicircle. All right. So what's the perimeter? I know it's 16 feet, so I wrote P equals 16 feet down. All right, so how do I find the perimeter of the rest of this? Well, I got two Y's. The left and the right side of the window are Y, and I've got the X on the bottom. Ignore the one and this one crossing over, and then don't I have to add on this semicircle perimeter? So I've got Y, Y, X, semicircle. So YY plus X, and then in the blue circle here, I've got pi times X over 2. Where did I get that from? Well, for this, I need half of a circumference. Half because it's a half circle. What's circumference? Pi times diameter. The diameter of this thing, as you see at the bottom here, is X. So pi times X. But I don't want the whole diameter. I only want half of it. I mean, I don't want the whole circumference. I want half of it. So that's why it's pi times X over 2. Okay, equals 16. Well, so then, all right, we can't deal with this X and Y baloney. We've got to get rid of one of them. So I decided to get rid of Y. So I took this equation and I got the X and the pi X over 2 over on the right side, and then I divided everything by 2, and I came up with this thing right here is the new way to write Y. So X is X, and this is Y. Now, can you get the maximum area out of this window? So how do you find the area of this? Well, it's the area of the rectangle plus the area of the semicircle. Area rectangle plus area of semicircle. So here's the area of the rectangle. X times my new Y. The area of the semicircle. What is that? Pi r squared. What's r? X over 2. So look up here way in the top right corner. Pi times the radius X over 2 squared. But I got to take half of that because I don't want the whole area. I want the area of a half circle. Square the X over 2 and you get X squared over 4. Pi times X squared over 4 over 2 is pi times X squared over 8. So area of rectangle plus area of semicircle. All right. So then I multiplied the X out. 8 times, X times 8, X times all three of these. All right, so now I've got that expression. And then you didn't have to do this, but because I had two X squared terms here, I created this, I factored the X squared out of those two. And that left me with this expression right here. All right, now I was in good shape to do a derivative. Derivative of 8x is 8. What do you do to take the derivative of this? These are all constants in this set of parentheses here. So you just do the power rule. 2 times the negative, negative 2, times that remaining constant, reduce power by 1. Derivative of this last one, 2 times pi over 8, which is pi over 4. Okay. Set derivative equal to 0. Here I actually multiplied 2 times these two parts inside. Anyway, I'm not going to bore you with every little thing here, but I came up with this answer in circle here, which simplifies down to, and well, yeah, this is probably the best I can get it right here. And if you do that on a calculator, you get 4.48 feet. So when x is 4.48 feet in this original plan here, that will maximize the area and yet keep the perimeter at 16 feet. So that was a little bit messy, and sometimes they get that complicated. By the way, what would y be? We'd have to come back here in this expression right here and substitute in that 4.48 feet, and you could find the height. So that may have buzzed by you. Were you able to pick that up? Do you have any questions? So let's go to the assignment. For 7, there are, there's a bunch of problems like the beginning ones where you don't, they're less complicated. Find two numbers that have this perimeter and have a maximum area. Those are more like these beginning ones here. 3, 5, 9, 11, 20, and then 4 more. 23 part C. Is that the one we did? No, we did. No, never mind. 23 part C, 33, 41, 47. So a total of, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9 problems for you to work on. Questions? All right. Well, I guess that's it. Thank you. I'll see you tomorrow.